Now we're going to take a look at one of the most powerful aspects of multi-objective analysis. Up till now, we've done some videos that show two-dimensional space and multiple objectives. We talked about the constraint method, talked about the weighting method, but that's not what's interesting about multi-objective analysis. What's interesting about it is that different people in systems problems have different objectives. That is, they have different measures of what makes one design better than another. And there's a terrific problem in the Civil Engineering Systems Analysis book by Revell, Whitlatch, and Wright. It involves management of the wastewater from a steel manufacturing plant. There's two types of wastewater that come out of the plant. One of them is called process water. And the other one is called pickling waste. And these result from the steel manufacturing process. Now, the steel plant needs to dispose of their wastewater, and they have a couple of options. They could send it to their own treatment plant, or they could send it directly into a river. What the word problem in the book doesn't do a good job of is helping students visualize the options. So that's what we're going to do now. We need a river, we need a steel manufacturing plant, and we need a water treatment option. So we have these two types of waste, and they can go in a couple of different directions. Let's call these arrows direct to the river, and let's call these arrows into the wastewater treatment plant. So we're going to need whatever the flow of pickling waste is. We're going to see how we can partition it into direct effluent into the river and treated in the wastewater treatment plant that then winds up in the river. You can begin to see some of the decision variables emerging from the sketch and some of the constraints. This node in our diagram and this node in our diagram will be balance constraints. Whatever the total flow of pickling waste is, it must be partitioned between these two streams such that these two streams add up to the total flow. So we may call that Q pickling that goes to the wastewater treatment plant and Q pickling that goes to the river. You can do the same thing for the processed water. We're going to get into some of the other parameters of the problem after we finish the diagram, but for right now it's important to know that we have 3 points of discharge to the river: straight pickling waste, straight process waste, or treated pickling and process waste. If the waste is treated, of course the strength of pollutant entering the river is lower. If they put it directly into the river, the steel plant spends less money treating the waste, but puts more pollution in the river. Now you might say that this isn't a multi-objective problem at all. The steel plant might operate under the idea that they want to minimize the cost of wastewater treatment while they operate under their permissible discharge limits. That is, there might be a regulatory agency that says you can't put any more pollution in the river than X. And as long as you're below X, you're free to minimize your costs. What the steel plant's intuition would be is to put as much pollution into the river as their permit allows, because this would minimize the treatment expense at the wastewater treatment plant. Well, it becomes a multi-objective problem when you recognize that there's also a government agency. So we're going to have the symbol of a government building over here, and they have a little bit different stake in it. The government, they set a discharge limit, sure, but they also collect a fee. They charge a certain price per pollutant. We could measure the pollutant. There could be lots of different ways to measure it. For example, it could be measured in BOD. It could be measured in milligrams per liter. But in any case, the steel plant pays money to the local government for the right to discharge pollutants into the river. And it doesn't matter whether they discharge them after treatment or if they bypass treatment. The more pollutant that goes into the river, the more the local government collects from the steel plant, and the more the steel plant pays. Now, we have this interesting problem. If we accept that the steel plant wants to minimize their costs, well, they first need to know what is going to be the fee. What's the tax or the fee that they pay for the right to pollute? This then becomes a parameter that the steel plant uses to optimize their decision variables. Notice that the boundary for the steel plant works like this. They get a parameter from the local government. They use that parameter in their own model to figure out how to minimize their costs without violating their discharge permit. But what's the government's objective? What are they trying to min? What are they trying to max? We don't know. There's a couple of choices. What if they were going to max their dollar? That might suggest a high fee. What if they were going to minimize pollution? That might also suggest a high fee. But if they were to set the fee too high, it might be prohibitively expensive for the steel plant to operate. Maximizing the dollars doesn't mean setting the fee as high as they possibly could, because the steel plant might slow down or cut back production. The government would choose a fee or a tax for the right to pollute in the river, then anticipate what the steel plant's optimization model is going to do, and adjust their fee based upon how the steel plant adjusts. So the government has a different decision variable. It is the fee. They must decide what to do with their objective function, and they have to anticipate the way the steel plant is going to operate in response to their fee. Now, there's one way to minimize the pollution, and that is to set the fee so high that it puts the steel plant out of business. That might not be the right idea. Perhaps you get minimum pollution because when they go out of business, there's no pollution, but there's also no jobs. If the government was going to maximize jobs instead of minimizing pollution, you might say production at the steel plant is a proxy for jobs, and so they would want to set the fee to allow the steel plant to maximize production. That fee would probably be zero. That fee could be negative. They could pay the steel plant to produce. They could subsidize the steel plant either through tax abatements or direct payments. That doesn't work either. The way this problem is set up, we have to understand that there are two problems, both involving the manufacturer and the government, and there's an interaction between these problems. The government anticipates what the manufacturer is going to do, and the manufacturer has their own objective. Meanwhile, the manufacturer responds to what the government is going to do. The government can really blunder here. They might be trying to maximize their tax revenues and put the fee so high that they run the steel plant out of business. So the government needs to empathize. They need to adopt the perspective of the steel manufacturer in such a way that they operate or they can understand the steelmaker's perspective. Even though they don't adopt the same objective as the steelmaker, they must empathize, adopt the steelmaker's perspective so that they can get what they want out of the steelmaker, knowing that their decision variable creates a difference in the model and changes the steelmaker's best set of decision variables. Then whatever the steelmaker does, that's how the government collects its revenues, and of course, that's the way the pollution in the river is dictated. The most interesting thing about multi-objective analysis is that there's both perspectives from two different people. They do not have to agree on the goals for the overall system. They could, and they could choose to cooperate, but they can also have their own separate decision variables, own separate objective functions, and come to a mutual accord that works for both of them. That's what's interesting.